How's it going, ladies and gentlemen? Mr. Donahue here again. This time we're going to take a look at some practice problems for 20.5, spontaneity of reactions. So objectives being to describe the spontaneity of voltaic cells based on the EMF, the electromotive force, and calculate the change in Gibbs free energy. So here's the equation, featured equation of the day. Delta G equals negative NFE, where delta G naught is the change in Gibbs free energy, N is the number of electrons being transferred. Here, the coefficients matter. All right, so we've ignored them for calculating E, but when we're calculating the delta G, we need to account for how many electrons are being transferred, so the coefficients do matter. F is the Faraday constant of 96,500 joules per volt mole, and E naught is a cell potential. Right, if you do that, and then note a positive E naught will result in a negative delta G, both of which are spontaneous. So that's kind of a way to check things if you're wondering about if it's spontaneous or not. So number one, the relationship between the change in Gibbs free energy and the EMF of an electrochemical cell is what? So this is just basically what is that featured equation of the day. It's right there, delta G equals negative NFE. All right, it's none of those other ones. Number two, which of the following reactions will occur spontaneously as written? So we're looking for things that result in a positive voltage, a positive EMF. All right, so let's check them out. Fe plus 2 becomes Fe0. Well, what is that process? I look at my chart, and it has a negative 0.440 volts, and then Fe plus 2 also becomes Fe plus 3. So that's the oxidation. So I got to find that process. But then I got to flip it because it's going in the opposite direction. So negative 0.440 and a negative 0.771, which is going to give me a negative E. So it can't be that. Let's move on to number two. I'm sorry, choice B. Let's check it out. 3Fe becomes Fe plus 2. All right, the Fe plus 2 looks like this process, but in the opposite direction. So I got to change the sign here. And I end up with a, do I gotta change the sign? Yeah, a positive 0.440. And, well, let's see what's happening with chromium. It goes from plus 3 down to 0, and it has a voltage of negative 0.74. So a negative 0.740, which when I combine those, I end up with a negative overall, right? And like a negative 0.3. So it can't be choice B. Let's check out choice C. I have tin plus 4 becoming tin plus 2. So that's a reduction, and I find it right here. So it has a potential of a positive 0.154. And let's see what's happening with the other thing. Chromium starts at 0, goes to plus 3. So it's the opposite of this process. So it's a positive 0.74. When I combine those, I end up with a positive E. So it's looking like C is pretty good. Let's check the rest of them. Tin plus 4 becoming tin plus 2. Where do I see that? I see that right here, and it's exactly how it's written. So I just use that positive 0.154. And let's see what's happening with the rest of the reaction. Fe plus 2 becomes Fe0. It's this process, which has a negative 0.440. When I combine those terms together, I end up with a negative overall. But hey, wait a minute. This one's weird too, right? I have two things getting reduced. I have Sn plus 4 becoming plus 2, so it's reduced. I have Fe plus 2 being reduced to Fe0. This cannot happen. You can't have two things being reduced, because what is reduction? Reduction is gaining electrons. You can't have two things gaining electrons. One of them has to lose an electron for the other one to gain. So D, not going to happen. And if you take a look at choice E, I think it's the same situation. Hey, tin's going from plus 4 down to plus 2, and iron's going from plus 3 down to plus 2. So you can't have two reductions. You can't have two oxidations. It's a redox reaction, reduction and oxidation. You can't have one without the other. And you can't have either of them twice without the other one. Right, number 3, the standard cell potential of the reaction below is positive 0.126 volts. What is the delta G naught for the reaction in kilojoules per mole? All right, so we know that delta G equals NFE. So they told us the E, the F is a constant, we're trying to find delta G, so we're also going to have to figure out how many electrons are being transferred. So if I take a look, PB is going from 0 to +2. So I know that's a 2 electron process. If I take a look at the 2 hydrogens, they're going from +1 to 0, and that happens 2 times. So sometimes you can get away without breaking down the half reactions, and you can kind of look at the equation. This one, I'm able to do that. I can see that there's 2 electrons being transferred. PB is losing 2 electrons, and each of those hydrogens is gaining 1, and there's 2 of them. So there's 2 moles of electrons being exchanged. Now, the F, the Faraday constant, is at 96,500 coulombs per mole volt times by 0.126 volts, positive 0.126 volts. So when we multiply all that together, we end up with 24318 joules per mole. Now we got to do sig figs and also convert to kilojoules because they specified kilojoules. So that's really 24.318 kilojoules per mole. But now I got to account for sig figs. You might think that this 2 only has 1 sig fig, but this is an exact number. You've counted exactly 2 electrons. It's not a measurement, it's exactly 2. So it has an infinite number of sig figs. The 96,500 has 3 sig figs as I used it, and then so does the 0.126. So I got to round this to 1, 2, 3 sig figs. Let's see what's next to it. I end up with 24.3 kilojoules per mole. And it's positive. No, I'm sorry, I lied. It's negative. I forgot the negative. Y'all were gonna let me finish that problem without having the negative in there, right? So spontaneous, there we go. Number 4, the standard cell potential for the reaction below is negative 0.55 volts. What is the delta G naught for this reaction? So again, delta G equals negative NFE. So let's take a look at the equation to figure out electrons. It looks like I2, 0 is becoming 2 I minuses. So that's a 2 electron process, but let's check the other one. I got 2 Br minuses becoming Br2, 0. That's also a 2 electron process. So I know that the Br minus is giving 2 electrons to the I2. So the whole thing is 2. So negative 2 times that 96,500 coulombs per mole volt times by the voltage of negative 0.55 volts. Now when I plug and chug and get the answer, I get 106,150 joules per mole. And if I round that to sig figs and convert it, oh no, I don't need to. It's just in joules per mole, so I don't have to do any conversions. I end up with, let's see, 1 sig fig, 2 sig fig, see what's next to it. It's a 6, so it rounds up. 110000 joules per mole. If you were to put that in scientific notation, it would just be 1.1 times 10 to the 5th joules per mole. Let's see, 1, 2, 3, 4, 5. Yeah. So there you go. Written either way is acceptable. Number 5, the standard cell potential of the reaction below is negative 0.34 volts. What is the value of the delta G naught for the reaction in kilojoules per mole? So again, delta G equals negative NFE. So how many electrons are being transferred? Well, it looks like Cu0 becomes Cu plus 2. So that's, I know that's a 2 electron process. 2 H pluses becomes H20. So it looks like copper's losing 2 electrons and giving them to the H pluses. So it's 2 moles of electrons times that 96,500 coulombs per mole volts times by a negative 0.34 volts. When I plug and chug, I get, 65.6 kilojoules per mole. I skipped the conversion factor to get kilojoules because I think y'all get that by now. And it is a positive value because we have a negative here and a negative here. So when you multiply 2 negatives, you get a positive. There you go. Number 6, the standard cell potential of the reaction below is positive 1.34 volts. What is the delta G naught for the reaction? Oh, got a multiple choice one. Okay. Well, we know it's delta G equals negative NFE. And let's think about this. I know that since I have a positive voltage and a negative there, I know my delta G should be negative. So I can eliminate two of these right off the bat. And then, all right, let me figure out how many electrons are being transferred. Well, I have 3 Cu0 becoming 3 Cu plus 2. So I know that there must have been a total loss of 6 electrons. Let's check to see if it makes sense with the Mn. I know each oxygen's minus 2. There's 4 of them, so I get a minus 8. I need a minus 1 overall, so there must be a plus 7. So Mn is a positive 7, and then over here, let's see, oxygen's minus 2 each. It's minus 4, means I must have a plus 4. So Mn is plus 4. So it goes from a 7 to a 4. Well, that's 3 electrons, but it happens twice. So yeah, 6 electrons is definitely my N. So I get delta G equals negative 6 times 96500 times positive 1.34 volts. And when I plug and chug, I end up with, let's see, did I write it out? I get that's a positive, negative 776,000 joules per mole. And whoever made this practice problem, it was me. Probably should have put units on all those things, right? It didn't even specify. A lot of times delta G will be in kilojoules per mole, but it didn't say. Anyway, but hey, wait a minute. It's a positive value. If there was a negative version of that, sure. So it's none of these answers. All right. So I hope you found that helpful. I'll see you in class. Okay, bye.